All right. So thank you everyone for attending today's Tea Talk. Today we have Alex Gagliano joining us from the University of Illinois and the CCA. So Alex studies the relationships between transients and host galaxies. And today he's going to talk to us about fast transient studies with survey streams. So Alex, I'll let you just take it away from here.
Great. Thanks, Dana. Thanks everyone for coming. I recognize that a virtual talk at the end of the day might not be the most appealing thing to attend, but I appreciate you coming. And admittedly, in hindsight, I recognize that this is an ambitious title. I don't claim that I'm going to solve this in the next 45 minutes. So perhaps a more realistic title is how we better enable fast transient studies with survey streams and what we might be able to learn from them using the host galaxies of explosive transients. I would love this to be as interactive as possible. I recognize that it's hard to keep your video on, but please ask questions whenever you have them, and I'd love to answer them to the best of my ability. Okay, so here's how my talk is structured. I'm going to start off with some background and motivation about why we might want to enable fast transient studies, although probably need less motivation with this audience specifically than with other audiences. I'll then talk about some work to enable real-time classification using the host galaxies of different classes of supernovae, using statistical correlations from a catalog called GHOST that I've consolidated from past discoveries. And I'll then narrow in on a specific study of a supernova called 2020 I as a case study of what host galaxy information can give us in the way of a detailed progenitor study of one event in detail. I'll then extend some results from the GHOST catalog that I had constructed, now a catalog called SCOTCH, in order to better simulate the types of events that we're going to find with upcoming higher redshift surveys, and then end with some conclusions and take questions at that time. Okay, so start off with the motivation. Historically, of course, the way that supernovae have been studied is an explosion goes off, we obtain a spectrum of that explosion, and from that spectrum, we classify it and derive certain properties about both the explosion and the progenitor system that exploded in this dramatic fashion. And this is getting much, much harder to do. So I have typically given this talk to LSST crowds where people are thinking about photometric classification or upcoming surveys, but with an audience that's very ZTF oriented, it's a really nice reminder that photometric classification is very necessary, not in the future, but right now for the data that we're ingesting today. So here is a video that hopefully helps illustrate that point. I have a mall-wide projection of the sky on the left, on which I've overlaid different candidate supernovae from 1800 to today that I've colored by whether or not they've been spectroscopically confirmed. This is from data from the Open Supernova Catalog and the Transient Name Server. So I'll play it and then I'll go back and talk about it in a little bit more detail. You can see that most of the events are blue. We've spectroscopically confirmed the majority of them. And in the last couple of years, you see there's just an explosion of events that are pink that we haven't spectroscopically confirmed. This number is a little bit overinflated because it's all candidates that are reported. Some of these will not be supernovae, but needless to say, it's getting harder and harder to study using spectroscopy all of the events that we observe. And you can see the probability density on the right as a function of redshift. It makes sense that the high redshift events are the events for which we don't have spectra, right? You want a high signal to noise and you want events that you can study in detail to uncover their progenitors. But if we really want to push our understanding to higher redshift events, then we just need to do well at photometric typing. We're not going to have spectra out in these domains. Another thing from this video, what I think is cool is you can see the SDSS2 Stripe 82 supernova survey highlighted right here of all the photometric events at high redshifts that are detected. And you can also see this big hole here. And I'll just overlay the ZTF data release 3 footprint. You can see the extent to which ZTF has really dominated in this, this set of alerts in this discovery domain. So hopefully that drives home the point that we need photometric typing of new transients, in my case, predominantly supernovae. And now there's a question of why you might want to do it quickly. So here is a plot of the phase space carved out by different classes of transients. No doubt many of you have seen lots of different variants of this plot. Here's one from the LSST science book, and luminous supernovae are in the red box, top right. You see there's a big question mark of a region in this phase space of faint, fast events that we have not traditionally been good at detecting. And the question is, with our current and upcoming surveys, are we going to get better at carving out that phase space? We're already starting to push toward that bottom left corner for unique classes of events. So things like FBOTs, belts, RETs, ILOTs, all of these have, there's a zoo of different acronyms to describe phenomenologically the different events that we've seen without yet uncovering the physical systems that drive them. But in my case, I'm interested in fast phenomena. That is to say, not necessarily unique classes of events that evolve quickly, but features of classes that we know relatively well, and those features which occur at early times and evolve relatively quickly. So things like shock breakout, shock cooling, CSM interaction, and companion interaction. Each of those could be talks in and of themselves, but if you have questions about how any of them work, I can go over them. So my question is, how do we enable fast photometric searches in order to discover some of these phenomena in supernovae and study them in detail to uncover the nature of progenitor systems? And in the way of real-time photometric classification, one of the really pioneering papers was this paper on RAPID by Daniel Multikrishna in 2019. And RAPID worked using a recurrent neural network that allowed for adaptive real-time inference. Essentially, every time you get a new data point in, the predictions of whether you were looking at a given supernova class would update. And so here's a video from the RAPID website showing simulated ZTF observations relative to trigger. And you see that you belong to this pre-explosion class up until trigger. And when you start getting some real observations from the event, then all of a sudden your probability of belonging to a traditional type 1a supernova jumps up here. So this is real time in the traditional sense, but RAPID was trained on simulated data, and it turns out does not perform super well on real data. And the reason for that is because of its reliance on uncertain photometric observations in a supernova light curve at early times. Basically, if you have bad seeing, depending on the cadence of your survey, all of these things can really mess up your very early time predictions. And with RAPID, the reason why you're entirely reliant on the light curve itself is because RAPID is constructed to assume this pre-explosion class before the trigger, and all of the other class predictions are suppressed up until your trigger. And so this eliminates any prior information that we might have about where and when supernova might occur. So we can hopefully improve real-time classification efforts if we take into consideration some of this prior information and reduce the dependence on these first early time photometric observations. And this prior information can come in the form of host galaxy correlations. So host galaxy correlations are things that have been known about for a fairly long time. They can aid in a litany of different studies. On the left, I'm showing a plot from a DES paper of the cumulative fraction of the stellar masses of host galaxies of different classes of transients. And the error bars are pretty large where the samples are small, but the big thing to notice here is that these cumulative fractions look different for different classes. So the really extreme cases are on the very left. The pink cumulative fraction corresponds to superluminous supernovae, which are statistically found in smaller, brighter star-forming hosts. And on the opposite side, you have type 1a supernovae that are statistically found in more passive, massive galaxies. These are kind of a proxy for the typical ages of the stars that you might find within those galaxies. And so this says something about the nature of the progenitor, at least at a statistical level. And then the other one I've thrown up here is type 1bc supernovae are found predominantly in metal poor galaxies and star-forming regions. And all of this prior information we have well documented in the literature, and we can take advantage of to improve our early time classification where data is sparse or where the signal to noise is not so high. And to explore the value of host galaxy information for classification, I will talk about the ghost sample that I've constructed. But first, I'll stop there and ask if there are any questions. Okay, if there are none, then I'll move on. So in order to construct a catalog that we might use to explore classification of supernovae using host galaxy properties, I've constructed GHOST. The details of it I won't go into now, but I matched the host properties from pan-stars for about 16,000 supernovae from the Transient name server and the Open Supernova catalog. And at the time, this was late 2021, this corresponded to about 78% of the events from those catalogs. And I launched a remote server with tools for exploring that catalog. I should note that this website is down right now, so please don't go to it, but it's down because Peter McGill, who's a postdoc at UC Santa Cruz, and I are collaborating on an extension for GHOST where you can both interact with the host galaxies that have been associated and also on the fly calculate derived properties using a backend SED fitter based on Prospector. And that is currently in preparation. So hopefully we should have that website launched soon. But when it was launched, this is what the website did. You could very quickly look around for the host galaxies of different classes. You can click and it would provide information from NED and from TNS and OSC about properties of the host galaxy and the supernova. And the classes of each of the events correspond to the colors of the outlines of these images. So we built this big catalog, GHOST, and we can then go about exploring the statistical properties of the host galaxies from the pan-stars catalog. I had a discussion with Dana earlier today about how you might go about associating transients with host galaxies, and it's something that I'm really interested in. So I ended up adding this slide at the last second. But in supernova studies, what is traditionally done is a method called the directional light radius. And that essentially takes the distances between the supernova and lots of candidate host galaxies around that supernova. And it normalizes all of those distances by the radius of each candidate host in the direction of the supernova. And the thought is this normalized distance metric could account for the intrinsic fact that you'll end up with larger separations statistically when you have larger host galaxies. So this is to kind of correct for that bias. The problem is this method really relies on accurate host galaxy radii at the catalog level. And so on the left, you can see where this really goes wrong, where you have this whole thing is one host. You have spiral arms that are kind of fragmented into these H2 regions, these clumps. And in pan-stars, each of those are reported as different sources, and their sizes are horribly estimated because the source fragmentation algorithm struggled to identify it all as one object. So this is where directional light radius really goes wrong. And for this work, I created a method called the directional light radius, which uses the postage stamp directly of the field. And it takes the brightness of the image at the location of the transient and traces it to a local brightness maximum, which, if you've done it right, should correspond to the center of the true host galaxy. Now, the devil's in the details here with exactly how you choose your step size for the algorithm and how you pre-process that image in order to highlight the the light profiles of the galaxies in the field instead of the clumps in, for example, the spiral arms. But in some early tests, we found that gradient ascent did slightly better than the directional light radius at low redshift for these big, bright objects that are well resolved in surveys like Pan-STARRS. And I'm currently working with a team, part of the Alersi broker system, to develop a deep learning solution to this association method as well. So the final big result, again, this is a very simple method, but we trained a random forest model on all the Pan-STARRS properties from the GHOST catalog. And we found that we were able to achieve a mean accuracy of just under 70%, distinguishing between core collapse and type 1a supernovae from the GHOST catalog using only the photometry and the second order moments of the host galaxy, but also so there's an asterisk at the using host info because we did take into consideration the radial offset of the supernova with respect to the host galaxy center as well. And we started looking into classification predictions as a function of redshift. And it turns out this was really hard to do because there are so many heterogeneous surveys that have discovered supernovae and reported them to TNS and OSC that make it really hard to distinguish between what's going on from all these different samples kind of mashed together. So we would like to do this again on a more homogeneous sample with untargeted searches to exactly see what it's learning between the two classes of supernovae. But for this sample, we constructed a feature importance plot. And you can see that the top features from the model, you can, to first order, group into 3 distinct categories. And those are features which correspond to the angular offset of the supernova in its host galaxy, 5 related to the color of the galaxy, which can tell you something about whether it's an early type or late type galaxy, and then some basic information about the light profile and morphology of the galaxy, which of course also may serve as a proxy for early or late type. And all of these have precedence in literature, so this is encouraging that this host-only classification actually does learn meaningful correlations between the host galaxy and the transient itself. And we are now extending this work using the derived host galaxy properties from a simulation that I'll talk about a little bit later in this talk. This is the work that I'm doing at CCA with a couple of people at top right, including Dan Foreman-Mackey, Gabby Quintardo, and Shirley Ho. And so on the left, as we talked about before, we have the rapid light curves here and the classification probabilities. Before trigger, you have very low probabilities of belonging to any of the classes by design. And on the right, we're trying to build an analog using a recurrent neural network that takes into consideration host galaxy properties. And again, these are very preliminary plots, but I wanted to show them anyway. To first order, you see that you can get some information about the classification probability before the trigger occurs from the host galaxy information. Now, this is, of course, very simple. We've included derived properties and it's a simulation. And so it's a big question how it'll operate on real data, and observed properties like the photometry and second order moments of a galaxy. We're now working on translating this, this model to more realistic data. And I'm the PI of 2 programs in 2022A to get Gemini spectroscopy of events found early. Hopefully, if we're able to use this to improve early classification, then we can trigger on some events that we find and get early spectra. And I want to talk about what we might be able to do with early spectra, but I'll stop there and see if there are any questions.
I had a question in the previous slide.
Sure.
Before trigger, let's at minus bottom left, bottom right, minus 150 days. Yeah, there's no new data there, right?
You have non-detections. So on the top, there are non-detections. Obviously, those are only obtained after you have the trigger and you know to look back for the non-detections.
But why is it fluctuating if there are no detections at all?
Right. So it's trying to read something into the noise of these non-detections, and where there are data gaps, then it relies more on the host galaxy information. So you see that in this case, it's trying to read from these non-detections, and it says that it might not belong to a type 1a, and then you have the data gap where the derived properties tell you you're more likely to belong to a type 1a. You get non-detections and it says maybe not, and then you have the real detections and you say, okay, it turns out you're a type 1a supernova.
Yeah, there seems something fundamentally, at least philosophically, incorrect to me, that if given zero information, you still have fluctuation in your deduction. So there's something odd about that. Maybe it's a question of how you want to weight what's the point of inferring something when given junk?
Yeah, that's a really good question. So these plots we initially made in order to see the added value at early times of host galaxy information when you don't have information from the light curve itself. But I will admit that in the updated runs, we've truncated it at 0 days from trigger, and we're now doing a direct comparison with and without host galaxy information at the very earliest epochs after trigger. But this was just a proof of concept to see when we have no light curve information at early times, do we actually get some non-negligible probability from the host galaxy information?
Yeah, no, I understand that. The basic point is good one, that you're saying if it is a spiral galaxy, it's more likely you'll see certain kinds of supernovae and less likely you'll see some other kind. But that inference should remain steady with time until you actually get any new data. So you may want to somehow put some penalty factor when the input data are essentially have carry no information.
Yeah, that's a great point. So in this model, like I said, because we're porting over to going from trigger onward, the thought is that you would have valuable information, but of course you might end up at like a late epoch where you have non-detections and then the predictions are still fluctuating based on that data. So a penalty factor based on the non-detections, I think, would be really interesting to look into.
So I have a question.
Sure.
Are you able to, based on your classification scheme, are you able to identify outliers? So things that really don't fit with either any of your categories that are established?
Yeah, this is a really good question. So for a lot of this project, we were looking into early time features of classes that we know well. The thought is if you don't have statistical correlations to train on, to learn from, then you're not going to do a good job picking out those events from host galaxy information, potentially. However, let's see, maybe I can jump a little bit later. Yeah, so we initially did dimensionality reduction using a principal component analysis for the ghost sample. And this is before we just separated out into core collapse and type 1a supernovae. And we found this weird clump of host galaxy properties. This is again using only host galaxy properties in the principal component space. And those ended up being outlier supernovae within the sample itself. So it is possible that you might find outliers of dominant classes by doing something like this, but this was very preliminary and should be investigated in more detail. We didn't look more into it.
Cool, thanks.
Mm-hmm. Okay. Let's see. Great. Now I'll talk about what we can do when we have early classification and follow-up and detailed spectroscopy for an individual event. So I want to highlight supernova 2020 OI, and this was a type 1c supernova that happened in the nearby galaxy M100. This was classified as a traditional type 1 supernova, so not a broad line or anything like that, but it turned out to be interesting for a variety of reasons. Here I'm showing the core of M100 in pan-STARRS imaging. This is the same data that we used for all of the ghost analysis that I showed on the previous slides. But luckily, 2020 OI was found in a galaxy where we have a lot better data. So this is the data that we get from Hubble for this same region. A lot of things to note here, but one of the most significant things from this picture alone is that you now resolve a stellar cluster at the location of 2020 OI, and this ended up being really interesting in our analysis. And we also have Muse IFU spectroscopy of the core of M100 that we leveraged to analyze exactly what's going on in the case of this explosion. And it turns out the early follow-up of 2020 OI yielded some interesting results as well. So we triggered it early, we followed it up with an external program, and we found a tiny little bump, an excess of flux, in excess of what you would expect given a traditional fireball rise model for 2020 OI. And it's a very subtle bump, but we have produced the data many times and convinced ourselves that it's real. There is a consistent excess across multiple bands and spanning multiple observatories. And then this suggests that the origin of this bump is physical, but it is a very subtle one. And so we sought out to investigate what caused that early time bump in the case of 2020 OI. I should mention that at the end of this gray highlighted region corresponding to the flux excess, we also obtained a spectrum, and that spectrum was really interesting in revealing some information about what caused that bump. So initially we thought potentially we're just dealing with shock cooling, which just shock cooling. Shock cooling is very interesting in and of itself, but we ran some models, and it turns out all of our models were inconsistent with the data that was provided. And it turns out that there was a very early ZTF observation that rendered these models invalid. You see the point in let's see, V band all the way, or sorry, it's R band on the right. There's almost a day offset between the initial observation from ZTF, which is very well constrained, and the bump itself. And none of the shock cooling models from literature are able to reconcile a gap between the start of the explosion and a shock cooling emission of almost a full day. So this suggests that we're not looking at shock cooling, potentially we're looking at something else. A basic description of shock cooling is on the left. You have the shock wave from the supernova that propagates outward. You get heating of either the surface of the star or the surrounding CSM, depending on the optical depths that you're looking at. And then a cooling of that material as it expands might cause an early time signature. But again, these timescales seem to be inconsistent with that excess that we observe. And I mentioned the early time spectrum that we obtained. In a lot of respects, this event was like supernova 1994I, which was this like characteristic type 1c stripped envelope supernova. But if we assume the same density model at different epochs in the explosion, fitting the spectra, we find very strong agreement on the right for all of the epochs after the first spectrum, and very bad agreement for the very first spectrum. You see an excess in density past what you would expect from the 1994I model. And on the left, we fit the very early time spectrum to, so CO21 is what was fit to 1994I. The naive CO21 model provides not a great fit. And if we then add an additional mass component onto models which are run in TARDIS with a composition distinct from the rest of the explosion, then we find much stronger agreement. And we've tweaked lots of different parameters, and it turns out preliminarily the composition which best fits for this very early time spectrum is enriched in lighter elements and has a small mass component in addition of the star itself. And so this suggests that there's an overdensity of lighter elements. This is things like carbon and potentially helium, although we didn't get a a bona fide spectral signature from the optical spectrum at the highest explosion velocities, so at the very outermost radii of the explosion. And it suggests that potentially there's some surrounding material from the star that the explosion collided into. And we constrained the nature of the progenitor system using a combination of data sets and models, some from the event itself, some from the host galaxy. So from the top, we used the bolometric light curve fit to a couple different models to constrain the underlying parameters of the explosion, which we then compared to the BPAS simulations of single and binary stars. And we constrained the models that at explosion time match the explosion parameters, the nickel mass, ejecta mass, and total energy of the explosion. And then we also did SED fitting in prospector for the stellar cluster coincident with the location of 2020 OI that could potentially give us an upper limit for the age of the progenitor star itself. And when you combine all of that information, you get a pretty consistent picture, which is, in the case of stripped envelope systems, it's still kind of an open question whether the envelope of the star becomes stripped in strong stellar winds from a single star, or from a binary system where the companion is stripping the primary itself. And so in this case, all signs point to a binary system with some surrounding CSM, but exactly the configuration of the CSM we're not able to say from the data set that we're able to obtain. But in this case, it's very clear that we're dealing with a binary system and actually one of the lowest masses for a primary for a type 1c supernova that has ever been detected. As for what caused the early time excess, we explored a lot of different models. There's no smoking gun, so the question is still up in the air as to what caused it, but it seems like what's most likely is that past the initial shock wave propagating through the star and the CSM, there was some ejecta CSM hydrodynamical interaction at later times, and that's what you're seeing, which is what could potentially explain the latency between the initial start of the explosion and the early excess. But there are specific MESA models being run by collaborators right now to actually explore that configuration in further detail. Okay, so my last phase of the talk, but I'll stop and take any questions about 20 LI. Okay, let's dive right into how we might go about simulating data that's potentially more realistic than the ghost data set that I constructed. Because of course, if we base all of our algorithms on data that has previously been detected, then we're limiting ourselves and unable to translate that software to things that we might want to detect in the future. So the work that I'm doing to simulate transients extends work that was initially put in place to develop the plastic challenge. This is the photometric LSST astronomical time series classification challenge. It's a bit of an acronym, but it was launched in 2018 on Kaggle. Its goal was to develop photometric classifiers for different classes of events. Full phase LSST-like light curves were given to classifiers who were tasked with optimizing various metrics for classification. And here's a breakdown of the training sample on the right. One of the important things to note about the plastic data set is that no host galaxy correlations were encoded within the data itself. Only host galaxy photometric redshifts were. And so in trying to extend this and explore the value of host galaxy information, we've created the SCOTCH catalog. That's the synthetic catalog of optical transients and correlated hosts. And this paper is now in internal review in the Dark Energy Science collaboration. We took 13 extragalactic transients and their models from plastic, although these have been updated since the original plastic challenge was run. And we associated each transient with a host galaxy, taken into consideration literature-based correlations with photometry, color, and derived properties like star formation rate and stellar mass. So here's a breakdown of the catalog at right, and the different samples. Should be note, these are not meant to be realistic rates. This is kind of a truth catalog that is meant to train different algorithms based on the discovery rates that people expect in the future. So this would be post-processed on top from this original SCOTCH catalog. And in order to construct that catalog, what we did was we took some correlations from GHOST, from really popular classes that are well studied, well observed in GHOST, and we matched them to a synthetic galaxy catalog called CosmoDC2. CosmoDC2 extends to much further redshift ranges, much higher redshift ranges, and also contains many millions more host galaxies than the GHOST sample itself. So we use a nearest neighbors algorithm called Annoy, which is used by Spotify to give you similar recommendations to the song that you're currently listening to. It runs very quickly. And in our case, we're able to scale up the number of realistic host galaxies for different popular classes that look like the galaxies in GHOST, but extend up to higher redshifts and now contain millions of events by convolving these two catalogs. And so here are a couple of results from that simulation. Here I'm showing the plots of the star formation rate on the vertical axis, the stellar mass on the horizontal axis for different classes of transients. And the most important thing to note here is just that these plots look different. There are meaningful statistical correlations that could potentially allow you to distinguish between these classes. And so I'll just highlight a couple of these. Type 1 superluminous supernovae, as I mentioned at the very beginning of this talk, we'd expect to find in small star-forming galaxies, so push toward the top right, or excuse me, top left of this plot. Type 2 superluminous supernovae, these are core collapse events that you'd expect to find predominantly in active hosts. And you see this, we've encoded a cut above this specific star formation rate line. And then top right, this is a correlation that we've embedded from previous papers finding that AGN occurs statistically in higher mass galaxies than lower mass galaxies. And so all of these are signs that we've encoded correlations that seem to make sense based on the literature. And so I'll stop there, but I'll just say it's a really exciting time to be studying explosive transients. There are many surveys currently running and soon to be running that are going to investigate these properties in much more detail. And if we're able to characterize and follow up different classes of supernovae or other classes of transients, then there are lots of different things that we can do. So potentially better localized EM counterparts or localized GW sources and study the EM emission from the same sources. We can study at a statistical level now with larger samples, potentially higher redshift systems than ever before. And that isn't just higher redshift events, but as we now push out to redder and infraredder observations, we can find classes of transients that we've missed in the past, and we could potentially characterize their progenitor systems in unprecedented detail. There are already proposals that have been accepted for JWST observations to study the host galaxies of kilonovae in detail, and white dwarfs, for example, to study the progenitors of type 1a supernovae. And all of these are really exciting studies that we have to look forward to if we're able to optimize our algorithms for fast characterization and follow-up. So I'll end there and take any final questions that you might have. Thank you very much for your attention.
Okay, thank you, Alex, for a great talk. If there are any questions, please raise your hand. I don't see any hands raised yet. Oh, never mind. Shri, go ahead.
Yeah, this is the topic of your talk is important in the sense that we have undergone a massive change in time domain astronomy, in optical, I mean, where we used to be starved for events, and now supernovae or supernovae candidates are dime a dozen, I mean, literally. And so naturally, and even as a supernova aficionado, I would say, there's no rationale to say we should follow every supernova that happens. The question is, how much, what I call is, how much blood can you squeeze out of stone? The answer is 0, but maybe rhetorically, but here there is some amount of blood before when the supernova happens. And the question, and I've been thinking about this for quite some time without coming to any conclusion, there's some pretty straightforward stuff, right? You see let's say, bluish object next to a 2 arc-second nebula, which looks bluish itself. Okay, likely it's a core collapse, and so on and so forth. And you're quantifying that along with real data. Those prejudices are now being, which is a good word, by the way, are being quantified and algorithmized, if I could say that. But what I'm not clear on, and it's not a criticism of your talk, anything, I'm just loudly thinking, at what point is this exercise useful and what point it's not useful? By which I mean the following. It'll be useful if it turns out, based on the couple of first data points, I can really unleash a few orbits of Hubble I have because I really want to get the UV light, maybe some other mission. I have a few triggers and I want to use it because I really want to get there right then. Okay, extremely useful because I only have a few triggers. And on the other hand, if the opposite is I use it and it turns out to be, it's a prediction, it's got errors, and it turns out to be a dud, in which case I'll be very upset with the software makers. And this is the part I'm unable to sort out, and I was wondering whether you've given some thought.
Yes, I have absolutely given it a lot of thought. This is a great question. And my personal perspective on this, I think maybe is more broad than my work itself, but it's that if you adopt these algorithms without thinking very hard about the use cases of them, when you would want to use them and where they might fail, then you might not be surprised when you get results that are not what you expect. And I say that because selection functions in astronomy are a whole mess, right? And they're suboptimal, but people have been using them for a long time, right? You want to look at a big bright galaxy to make sure that you find some supernovae in order to justify the time that was given to you. And so for cases like that, I could see host galaxy information being very valuable in order to find a particular class of transient that you understand, whose correlations that you understand well, and in order to come up with a sample that whose characteristics you understand. But if you're applying it, trying to look for some really strange, rare event and just keeping your fingers crossed that it'll turn up something wild in that space, then I think you might come up short.
Well, I have another question, but I'll wait till I don't want to dominate. So this after this, Johan, I can come back if there is time.
Go ahead, Johan.
Hi, Alex. So you mentioned that you are the PI of 2 Gemini proposals to study the early explosions. So what type of early explosions are you most interested in? Are they all similar to the 20 OI or some other types?
Yeah, that's a really great question. So the 2 proposals, the first one is, let's see, I talked about it somewhere. Yeah, the first one is time we have on Geniers. So the spectroscopy I mentioned that we got with 2020 OI didn't give us a smoking gun signature of helium in that surrounding CSM. And a lot of the signatures that would be unambiguous helium detections would be detected in near IR spectroscopy. So that particular program is to study stripped envelope systems early to investigate this question of whether there's still surrounding stripped material near the star when it explodes. And the other big program that we have is early spectroscopy to find type 1a supernovae as early as possible in order to get high cadence light curves to build up our low redshift sample to better constrain cosmological parameters to counter the high redshift sample that we're probably going to get with upcoming surveys like LSST.
I see. Thank you.
Mm-hmm.
All right, I don't see any other hands raised. So Shri, if you want to ask your second question, go ahead.
Sure. So I was thinking, Alex, of turning this problem around its head in the following sense. We ask the question, we see a new transient and we look at contextual data and say, want to make some statements. How about the other way around? Just play along, let's play along with this idea. We see a new transient and we do the opposite, which is we'll say, I'm only interested in transients. Okay, let me be a bit naive, ridiculous and say, which are more than 30 kiloparsecs from the center of their galaxies. Of course, the more traditional cases, I'm more interested in transients at the centers of their galaxies, which is a very well-defined program, leads to tidal disruption events, and also maybe some very peculiar supernovae in the nuclear event. So in this case, basically, how do I put it? I'm not sure why one would do this. I can think of one use case, which is there's still a mystery of these certain supernovae which are only found in the halo, apparently. And but it's sort of a different approach where you're saying supernovae are so free and so freely available that I'm actually going to use them to say something about host galaxies. Sounds a bit strange, but anyway, I'm just sharing this wild idea.
Sure. Yeah, I didn't talk much about it in this talk, but I'm very interested in the machine learning aspect of all of this. And I think you could easily implement some kind of active learning framework where you have some like priors based on where you think different classes would occur. And then as you get more events in, then that could better inform like, oh, if you're only looking in the halo and then you find classes that you don't expect to find, then you could update your prior distributions for where you think those events could occur.
Are there any other questions? Please raise your hand. Alex, I have a question,
Sure.
which is with some of these classification methods that you are, hoping to implement with these large surveys. How much does having a bad data point matter? Like, have you explored what happens if you put in something that you think is, it's coming out of some data stream and it turns out to just be like completely wrong for something like a property of the host galaxy? Will you notice it, or will it kind of just happily do its classification?
Yeah, that's a good question. It's a question that I haven't looked into in detail, truth be told. The thought is these are statistical correlations. So you might wash over individual correlations that look completely different for a set class, right? If you expect type 1a supernovae to occur in big red early type galaxies, and then you find one in like a really small, bright star forming galaxy, then my classifier might just say, like, we don't think that's a type 1a supernova. And so yeah, that I think it would not do as well on for individual events. But if you're interested in the bulk properties of the class itself, then maybe it's okay that you don't find that one supernova.
Yeah, thanks, Alex. Okay, I don't see any other hands raised, so I think I will stop the recording. But if you do have any questions, you can stay on the line and ask them. So thank you everyone for joining, and thanks Alex again for a great talk.